Hello everyone. Today we will continue our discussion on phase diagram from thermodynamic principles. We are concentrating on binary phase diagram, and that too for solid and liquid ideal solutions. And today's lecture is lecture 14. In our lecture 13, we derived two equations from the equilibrium concepts, that is chemical potential of a particular element in a phase when it is equal to the chemical potential of that particular element in other phase at a particular temperature and pressure. We call it as chemical equilibrium, and that time we had two equations. The equations are written as equal to minus delta Z0 A solid plus RT ln XAS. This is one equation which was derived from the chemical potential of A in both the phases, that means liquid and solid, and the another equation was, there is RT term, RT ln XB solid equal to delta G0B liquid plus RT ln XB liquid. And these two equations were GA0, which is a pure condition for liquid, and this is GA0 for solid. This is GB0 solid, and this is GB0 liquid, and our temperature was less than TMB and TMA. The temperature is less than melting point of pure B and greater than melting point of pure A. So that case, so we got these two conditions. This is G1 of solid, this is G1 of liquid, and then we had this is for G2 of liquid, this is G2 of solid. Now these two equations, this is equation 1, this is equation 2, were obtained when we had a common tangent passing through these 2 points on liquid and solid lines, and this is corresponding to XB of liquid, this is corresponding to XB of solid, which can also be written in the form of XA liquid 1 minus, and this one can be written as 1 minus XB solid, since XB liquid plus XA liquid equal to 1. Similarly, XB solid plus XA solid equal to 1. And at this point mu A of liquid equal to mu A of solid, and here mu B of liquid equal to mu B of solid. So this expression was drawn from this concept of mu B of liquid equal to mu B of solid, and this one was derived by using this particular concept equal to mu A solid. So, this is clear. So, now we see that we have XB, XA solid liquid as well as XB liquid and XA solid, but everything can be converted in the form of one particular component. So, we can convert this into one particular component. For example, if we see this particular equation number 1, which is ln XA L equal to minus delta G0 A solid plus RT ln X A solid, which can be written in the form of, this is equation 1, X A liquid equal to X A solid exponential minus delta 0 A S by RT. This is equation 3. And then the another equation was ln RT ln XB S equal to delta G0 B of liquid plus RT ln XB liquid. So, this is equation 2. I can write this one as XB liquid equal to XB solid exponential minus delta G0 B liquid RT. This is equation 4. Now, remember that this notation delta G0 A S, this indicates that this S indicates that this we are considering with reference to solid solution, and when we are considering delta G0 B liquid, this is with reference to the liquid solution. But in both the cases, these two terms are indicating pure A or pure B. So, this one is for pure A and this one is for pure B, and remember in our previous lectures we have considered that everything should be with reference to the melting. Now, that is what this, I can write delta G0 A S equal to minus delta HM A Tm melting point of metal, pure metal A divided by melting point of pure metal A. So, this minus is coming because this term is basically the enthalpy of melting. For pure A. Similarly, delta G0 B liquid equal to delta HM B Tm B minus T divided by Tm B, and where delta HM B, I can put a 0 sign here because everything we are considering with reference to the standard, because the pressure was kept 1 atmosphere. So, this would be equal to enthalpy of melting for pure B. Now, if we add up equation 3 and 4, if we add them, so we come to XAL plus XBL equal to XAS exponential minus delta Z0 AS by RT plus XBS exponential minus B liquid by RT. Now from this particular expression, which is xp, this equation as well as this equation, if we see that this term leads to 1 equal to xas exponential minus delta z0 s RT plus exponential minus delta z0 b liquid RT minus x as exponential minus delta z0 bl by RT, because xas plus xbs equal to 1, that indicates xbs equal to 1 minus xas. So I am just replacing xbs with this term, and that is what we are getting, this equation. And then from this I can get to xas equal to 1 minus exponential minus delta z0 bl by RT divided by exponential minus delta z0 as by RT minus exponential minus delta z0 bl by RT. So this is solution for, this is one solution, I can put it as 5, equation 5. Now if I know xas, since we know this particular equation, xal equal to xas exponential minus delta z0 as by RT, if we go back and see that particular expression, this is the expression. I can replace xas with this particular expression. So then I replace it, this xa I can replace, so I can replace it as 1 minus exponential minus delta z0 bl by RT into exponential minus RT divided by exponential minus d delta z0 s by RT minus exponential RT. So this is xal. Now if we go back to this particular plot, these 2 points, actually we have solved these 2 points, the composition of these 2 points. Composition of this point, that means the point on liquid G2 line and point on solid G2 line, these 2 compositions can be denoted either by xbl or xbs, or it can be denoted as xal or this should be xas. So actually we have solved this particular composition and these particular compositions. That indicates that actually we have found out 2 points in the composition, in the temperature composition diagram, which is actually a phase diagram. So now if I get the expression for this as well as this, that means the composition for solid solution and liquid solution who are in equilibrium. So then if I try to plot it on a temperature versus XB or XA plot, this is pure B, that means XB equal to 1, this is pure A, that means XA equal to 1, and our temperature is T, which is less than TMB, that means if consider this is as TMB, melting point of pure B, and more than melting point of A. So, at this temperature, if I consider pure A side, then it will be all liquid, because T less than TMB greater than TMA. So, at this temperature pure B would be in solid condition, but pure A would be in liquid condition. So, if we have pure A and pure B, those points on the phase diagram would be this point as well as this point. So, now I can put it in green color. So, this is for pure B melting point and this is for pure A melting point. Now, in between we have solved XAS and XA liquid, that means the solid and liquid solution compositions who are in equilibrium. So, those 2 points I can plot these 2 points. Now, gradually if I try to see another temperature line below this temperature as well as above this temperature, and if we resolve this particular compositions of solid and liquid solution at that temperature following the method what we have described till now, we will see that those compositions will be lying here, and in this case it would be here and it will be here. So, now these lines, if I try to give a different notation, these lines are all XA liquid line and these line are all XA solid line. So, now if we, and at this point, so XB solid is merging with XB liquid and here XA solid is merging with XA liquid. Now, if we connect the composition liquid compositions, so I can connect those liquid compositions and I can also connect the solid compositions. What I am seeing? I am seeing a phase diagram where this portion would be entirely liquid and this portion will be entirely solid, and here liquid plus solid. And this phase diagram has been calculated from only 4 basic data. One is TMA, another one is TMB, then delta H MA0, delta H MB0. And this is possible because we are considering ideal solutions. So, these 4 basic data are used to find out the compositions which are in equilibrium. For example, if I consider, let us say this particular, we put it as a composition equation 6. So, this 5 and 6, if we see, we are actually using these 4 compositions, these 4 basic data, and we are getting the entire phase diagram, and these phase diagram we call it as isomorphous. Isomorphous phase diagram. Now, In this isomorphous phase diagram, what we have also seen from our earlier discussion, which was based on experimental cooling curve method. So, that time this line is called as liquidus and this line we call it as solidus. And at any compositions, if we take any compositions, any composition, and if we reach to this particular temperature, we can also find out the fraction of liquid and solid solutions which will be in equilibrium as well as their compositions. So, now for that reason we have to make use of lever rule, and if I consider this point it as M, this point is at N, and this composition is x 0 with respect to B, then if I put it this point as O, then the fraction of liquid would be equal to On divided by Mn, and that time the composition of liquid phase would be this one, composition would be Xm with reference to B, that is liquid composition. Liquid composition, and similarly fraction of solid would be equal to Mo by Mn, where Xn equal to solid composition. And remember, these fractions are coming from tie line construction, and that too the basis is mass balance. So, now from this entire discussion what we have seen that composition free energy diagram is actually leaving us to draw a phase diagram for the entire compositions range, and we have done it for ideal solution for solid and liquid phases and in case of binary system. So, now we can also see that this particular phase diagram has been drawn from the concept of chemical equilibrium, that is the chemical potential of a particular component in a phase is equal to the chemical potential of that very component in other phase, and that is the crux of getting to the solution of the compositions of liquid solution and solid solution which are in equilibrium. Let us stop it here. So, we will continue in our next lecture, where we would be able to see that if I take any compositions between pure A and pure B, and we can also predict that which phase would come out of what compositions, if we have an idea of free energy composition diagram. Thank you.